So the next talk is tighter adaptive IBAs and VRFs, revisiting what is the artificial abort by Hanamuka, Katsumata, Kimura, Tekamura, and Yamada, and Kawa will give the talk.
Thank you for the introduction. I'm Kaoru, and I'm talking about this paper. And this work is joint work with Goichiro, Shu, Kei, and Shota. First, I'll explain about our contribution briefly. Our main contribution is that we propose new analysis for partitioning-based proof using artificial abort, which provide a tighter security proof. By using our new analysis, we provide the following result. First result is that we improve the reduction loss of Waters IBE and ABB IBE. The second result is that we propose a new partitioning function for ABB IBE, which provide a tighter reduction. The final result is that we propose the first VRF with sublinear verification key and proof sizes under the standard delay assumption. From here, I talk about the partitioning techniques and the artificial abort techniques. In this work, we mainly focus on the decisional security model with Oracle queries. For example, the security model of IBE and the VRF is included in this type of security model. Specifically, in the initial phase, the challenger generates public and secret information, and it gives public one to the adversary. Then adversary can make Oracle queries adaptively. Then the challenger generates the answer by using a secret information. And typically, adversary makes at most Q queries, where Q is set as a polynomial of security parameter. And mobile adversary makes challenge queries. Then challenger pick the random bit B and generate a challenge from random bit and query queued. Eventually, adversary output B prime, and if B prime is equal to V, then adversary win the game. Then in this game, the advantage of adversary is given this equation, where SA is a winning probability of adversary. Then to show the security, we usually construct a security reduction, solving some computational problem which internally run the adversary. When we show the proof, then we sometimes use partitioning techniques. These techniques divide the space of queries into two spaces by using a partitioning function f. Specifically, f of q is equal to 0, then such query belongs to S0, and otherwise query belongs to S1. Then in the security reduction, the simulation can simulate the oracle only when the f of qi is equal to 0. And the reduction can embed the computational problem into the change only when the f of q star is equal to 1. And otherwise, the reduction aborts the game and output a random bit. Then now we want to complete the security proof by using these partitioning techniques, but this reduction does not work well in some cases. So now let's consider the case where we want to prove the security under the decision problem. In this case, the advantage of reduction is given by this equation. Then more concretely, the P of Q means that the probability that the adversary makes a query sequence Q, and SA and gamma, respectively, winning probability of adversary and no aborting probability of reduction condition the query sequence. Then notice that these first term and second term is are corresponding to the winning probability of reduction in no aborting case and aborting case respectively, condition the query sequence queue. Then we can rewrite this equation like this. Then the important observation is that the term in the red box fall into this interval between the -half to half. So for some adversary, the advantage of reduction may be negligible. This is a problematic case. To overcome this problematic case, Waters introduced the artificial abort technique. In short, the reduction at the additional abort step after adversary output B prime. Specifically, the reduction first estimate the gamma no aborting probability gamma by using Monte Carlo method. Specifically, it samples many partitioning function and count the number of partitioning function satisfying the aborting condition for fixed query sequence. After that, the reduction aborts the game with probability, this probability, where the gamma mean the lower bound of no aborting probability. In this case, the advantage of reduction is given this equation, and notice that the term corresponding to the no aborting case in previous equation is divided into these two first and second terms. Then we can rewrite this equation like this. So if adversary has a non-negligible advantage, then the reduction also has a non-negligible advantage. So we can overcome this problematic case. But the estimation of the no-aborting probability requires a very expensive computation. So this includes the running time of reduction. Eventually, it includes the reduction loss. So actually, the running time of reduction in the Waters analysis quadratically depend on the number of queries and inverse of advantage of adversary. So as a naive question, there is other analysis which can be achieve a smaller reduction loss compared with Waters analysis and existing improvement. Then, now we move to our analysis. In our analysis, we modified the artificial abort step a bit. It first compute the approximation value of no aborting probability by exploiting the structure of sequence of queries such that this condition holds, and the reduction about the game with probability, this probability. Then, in this case, the advantage of reduction is given this equation. Gamma chooser no longer cancelled out as well as Waters analysis. But by using a useful condition, we can get this lower bound. If we can ensure this condition for value D, then reduction has a non-negligible advantage like this when adversary has a non-negligible advantage. So now we are to get this condition. Then toward this, we exploit this observation that if the left side condition holds, then we can get a desirable condition. Then notice that the term in the letter box means that the gap between the actual no aborting probability and approximated probability. So this value means that can be regarded as an approximation error. So now we want the approximation with this accuracy. Then let's define these events. Then in the previous improvement by Beimel template, that is same, but they use a union bound to obtain these. Sorry, the direction of the inequalities should be inverse, but this inequality. Then they set the gamma tilde like this. Then the second term is corresponding to the approximation error. Then, but we have to get a more better approximation error. So now we use the Bonferroni inequality to get a tighter lower and upper bound like this. Then we set the gamma tilde like this. Then in this case, this third term is corresponding to the approximation error. Then we can get a more a better application error. Then in our analysis, we exactly evaluate this approximation error, and we set a parameter so that this condition holds. For example, in the context of orders IB, we can set a parameter so that gamma mean satisfies this condition. Compared with better recent pattern analysis, this need to set a gamma mean whole satisfy this condition, so we can improve the reduction loss for advantage. And of course, we have to compute the gamma tilde efficiently. Unfortunately, the naive way to compute this value requires inefficient time. But to overcome this, we exploit the generating function for orders IB, and we use a device independent hash for ABB-IB and VRF. Eventually, we can show that the running time of reduction linearly depends on the number of queries. Eventually, we can improve the reduction loss, and by using this new analysis, we can get our result I explained in the first slide. For the detail of our contribution and analysis, please see our full version of paper on ePrint. Thank you for the attention.